remember that's for the committee. Making this law.
Okay, so hello everybody, welcome to our first presentation of this semester colloquium. I'm very happy to introduce today Dr. Keshav Raja. He is a research faculty at the Center for Ocean and Monetary Study, COAMS, which is like 10 minutes in that direction. Here his PhD from the University of Grenoble, France in 2018. Where he worked on internal waves and wind flow in the presence of topography. And he's going to talk a little bit about that. And also, Keshav joined FSU last April after finishing his postdoctoral research at the University of Southern Mississippi. And today he will be presenting his recent work on some issues with data assimilation and ocean modeling. So welcome, Keshav.
Thank you, Olmo. So I said, I'm a physical oceanographer. Who studies internal waves. And I use ocean models with data assimilations as a tool to study physics of internal waves. So this is something that I started when I was doing a postdoc at University of Southern Mississippi. And now I'm at COAPS and continuing the same research, namely that there is some kind of issues with the data assimilation in the ocean models as it is implemented right now. And that is they're generating some spurious internal waves. I'm going to talk about what that means. So a brief outline of what I'm going to say. First, I'll talk a little bit about Earth system modeling, and this involves ocean models with data assimilation. This is just to set the context. And I'll introduce something called a model adjustment problem. This happens after the data is assimilated in the model. And there I'll briefly introduce what internal waves are in the oceans. And then this will set stage to discuss the spurious internal waves generated during a data assimilation in ocean models. And finally, I'll present an ad hoc solution, kind of like a quick fix to reduce the spurious internal waves, which was part of my work at COAPS in the last 5 months. Okay, so Earth system modeling. So this is the state of the art right now. It's coming from a paper which was published in 2022, discussing on what is the future of Earth system modeling is. So Earth system modeling, I don't know, I don't think I'll have to explain the importance of predicting our climate or Earth system for anybody who is living in the 21st century. Well, the predicting Earth system involves taking observations from around the globe, and these observations will not be will always be sparsely located in space, time, or in frequency, or in spectral space, and then using that observation to improve our modeling, which is based on equations that we already know. And so this is like a schematic of a fusion of models and observations that people are working, or we are trying to achieve. We are almost there. So we have observations coming from satellite radiance, ship tracks, and all kinds of ocean and atmospheric observations. And then it's put up in a retrieval system, and this can be used with the data assimilative system. It's a scheme to convert these observations into a format that can be used in the models. And these observations can be used to train the models, as what Olmo might work or is already working on, or it can also create empirical models. And this model can be used for predicting the Earth system, both atmosphere or ocean. And this has lots of applications, including predicting when and where our next hurricane strikes, or to even climate change predictions. And this model can be considered as a data cube, as it is called right now. That means that it's a cube of data which can be sliced in any direction. It's not a spatial cube. It's a temporal, spatial, or spectral cube, which can be sliced and study in any fashion we want. That's our aim. And this can also give like an observation simulator for further for directing further observations. So this is where we are headed for. So to improve this kind of modeling is very crucial as we proceed in our endeavor. So US Navy has their own Earth system model, which is almost operational right now, almost operational. So they have it all ready for launching. So they have an atmospheric model, which is called NavGem. So they have lots of acronyms here. Like it's a flooding of acronyms from here on. So NavGem means Navy's Global Environmental Model. It's an atmospheric model. It's the same kind of model as the National Weather Service has. And there's 60 levels of atmospheric layers with a resolution of 0.4 degrees. And yeah, there are lots of details here. And then the ocean component of this system model is the HICOM model. It's the hybrid coordinate ocean model. That's what I'm working on. It has a resolution of 1/25th degree. It's roughly 4 kilometers in the tropics. It's 41 layers, and it includes tidal forcing. And it's forced by the atmospheric model here as well. So all these three models are coupled. Sea ice is a model for ice in the polar region. And so all these three models are coupled. They give feedbacks to each other, and they are run in parallel. And for all these models, there is data assimilation as well. So for atmospheric model in the NavGem, there's a data assimilation, a 4D VAR scheme. It's called 4-dimensional variational scheme. I'm not going to talk in detail about the schemes of data assimilation, just give an overview of the data assimilation and the problems of implementing these data assimilation. And HICOM has a 3D variational scheme for assimilating data. And it takes a 24 hours window of data to assimilate, and it assimilates over 3 hours. IAU stands for incremental analysis update. Means that it puts this observational data over 3 hours of duration. Yeah. So what I work on is this aspect. So it's exactly the HICOM that they use for the Earth system modeling, but I only use the HICOM with 1/25th degree resolution, and the data assimilation from ENCODA. ENCODA stands for Navy coupled data assimilation scheme. Lots of acronyms. So this is an overview of the sequential data. Sequential means the data is assimilated as it is available. So it's like an overview of sequential data assimilation used in ENCODA. So it's kind of like schematic. So the green part is the forecast. This is the solution of the equations we have from the model. It's also called the forecast. And we have the observations at that time, which is in the blue. And then from these observations, we can calculate an increment that can be added to the forecast to create an analysis. So hopefully the analysis is closer to the observations from our forecast. And this happens in this time region, and this analysis becomes the initial conditions for the next forecast. And again, we have the observation here, create the analysis here, it goes again, and forwards. So here the analysis field, it's just like a simple equation where the analysis field and the background field is coming from the model, and an increment is calculated from these observational data. This is where the data assimilation scheme happens. So this is where most of the data assimilation research, including almost research on machine learning to improve the calculation of increments happen. But what I'm going to talk about is not on all those things. I'm going to talk about what the consequence of creating such an analysis field from this increments. So as I said, the data assimilated is within a window of time. So this TK plus 1 minus TK will give you the data over which it can vary. For Navy's ocean model, it's 24 hours. But you can have 6 hours or 3 hours, depending on what you have how much data you have and what you require. And for incremental analysis update, this increment that is calculated by the data assimilation model is not put into the model instantaneously, as I said. It's put through a few time steps, fractionally. So that is what it represents here. And then we can say we can have an incremental analysis update period, IAU period, over which the data is being assimilated. I'm just defining things that will come up later in my presentation. So here for the Navy's model, this T insertion was 3 hours. IAU period was 3 hours. That's user defined actually. So if you're running the model, you can define if you want to put it up in 3 hours or 6 hours. Okay, so this is the whole data assimilation system for the Navy's Earth system prediction capability. It's a very complicated system. I'll try to explain it. Don't worry about the text. I just put it here so that I don't get lost. I'll explain it. Yes. So this is 1 day, 24 hours in the model. So the blue, the yellow bar here shows the atmospheric data assimilation window. So for atmospheric model, it's 6 hours. So it takes the observations over 6 hours and then creates an update centered at this hour, and it puts up the data, the increments into the model over 3 hours. And then it runs the model as a couple forecast ocean atmospheric model for some time. And then from here, this generates a first guess for the ocean data assimilation window, which is 24 hours. So for the ocean data assimilation window, it takes the first guess from 6 hours of this couple forecast here, and also this long 18 hours of couple forecast from here. So that comes up here. So using these two, combining these two first guesses, the ocean data, the encoder or the ocean data assimilation scheme runs, and then it creates an increment centered at 12Z. And this is put into the system over 3 hours here. And then it goes on here for creating the first guess for the atmospheric data assimilation, and so on and so forth. So there are the system has to run the forecast forward to generate the first guess, and then come back and then add the increments over 3 hours. So it's not straightforward. It has to go back and forth. And all of these things are already optimized based on their own validations and tests. So I like determining how long should the couple forecast run to generate the first guess for the ocean data assimilation. These are all well researched by the Navy. Okay, so that's how the data assimilation scheme in the system model works. So the update that are generated by the data assimilation scheme need not be solutions to the model equations that we have in the model, because it's generated by encoder. The data assimilation scheme is just taking up observations, sparsely located observations, and then creating an increment that is to be added to the model. So it need not solve the equation. So the problem with that is that it is kind of like a non-physical forcing term on the model. So you're just adding something which doesn't solve the equation, so it goes into the right-hand side, which forces the model. And this forcing forces the model to undergo kind of an adjustment to restore the dynamical balances. And to just visualize how strong this forcing can be, this is a time series of density profile at a location in the Gulf Stream. That's where lots of eddy motions happen. So you have lots of data coming up in the North Atlantic. And this is a high simulation with DA. And you can see it's a 30-day time series. And you can see that whenever there is the increment that is being added, you see the whole ocean being pushed down like suddenly. It's over 3 hours, but still you see the drastic change in the isothermal. So it's kind of like a very strong forcing that happens while the increment is being added. And this forcing leads to adjustment of the model.
So I have a question.
Yeah.
I try to understand the semantics here, which is the difference between the forcing and perturbation.
Mhm.
So to me, the forcing is over time, you're trying to gradually force something, but that doesn't happen in the kind of perturbed way. It's gradual process.
Yeah.
Right, but you're injecting that kind of instantaneously, the corrections?
Yeah, over 3 hours, the IA.
Over 3 hours.
Yeah. So, yeah, I agree with it. It's a matter of wording. It's a perturbation.
Right, right.
It's a perturbation force. There is forcing through wind and the surface winds and also the other motions like tidal forcing. So this is an artificial.
Right, no, I understand. Yeah.
Okay, so we can calculate the imbalance created by this perturbation to the system. So, so I used the data from encoder. So we have the analysis fields and the forecast fields. And then I calculate the thermal wind balance. This is I'm not going to describe what thermal wind balance is. It's just a dynamical balance that we expect large scale flows in the oceans to maintain. And as I said, the updates need not solve this equation. So whatever is left is the imbalance. So I calculate the RMS of this imbalance in the x-axis and the y-axis. It's a two-dimensional vector equation. And then you can see that, and this is the difference between the imbalance of the analysis and forecast. So essentially, this is the imbalance created by the updates. Yeah.
So that's just before the data assimilation happens and
After that, yeah. So so the forecast fields is just purely from the model, and then you add the updates, and then you get the analysis fields. So I solve this equation for both the analysis and forecast fields, and then take the difference to get the imbalance added by that, and then I can get a map of it, and you can see that there is strong imbalances in regions that have high mesoscale activity. Mesoscale is like a few hundreds of kilometers of motions. So wherever there is high oceanic motions, you have strong imbalance created by the updates. And this is averaged over 30 days of data I have. So this is a big problem because it's pushing in lots of imbalances to the model at each update. I can also calculate the energy injected during this process. So what I did was to calculate the total potential energy difference between just before the increments are added and after. So this is the delta PE of the whole ocean in a simulation with data assimilation. It's the same HiCom simulation with data assimilation. And I also had a simulation without data assimilation that were run in parallel to create to calculate how much energy is injected just because updates are added. And then you can see that in the same regions where these are western boundary current regions, there is high energy injected into the model because of data assimilation. And it's over 3 hours. It's like a huge amount of energy just added. So this potential energy, this spurious potential energy, is what causes the adjustment of the model. And usually, this is not a new thing. This is everybody knows that if you add something, you need the model to adjust it for some time. So the adjustment process physically involves inertial oscillations. So these are motions that rotate in the. So Earth has a natural frequency, which is the rotation of the Earth. So these are motions that rotate with the natural frequency, which is called inertial frequency. These oscillations are called inertial oscillations. Mostly happens in the mixed layer, in the upper layers of the ocean. And then there can be some spurious mixing. And also there can be some baroplanic or barotropic adjustment. Baroplanic means it varies with the depth of pressure. And barotropic is constant with the depth. So hopefully these things die down in a few time steps or a few hours. So so after after data is being assimilated, you don't rely on the model output just after the data. They go a few hours there for all these adjustment processes to die down, and then you have the forecast.
So I have another question. Sorry about that.
No.
So Do I have the right impression that the bold-faced statements are essentially your ignorance about the physics that is in the model that we cannot capture?
No, these are consequences of.
No, I understand, but if you knew
Yeah.
the reality,
Right.
would your model actually not suffer from that?
If you are adding an increment, like, I mean,
You're
No.
adding because your model doesn't work.
yeah, essentially, that's why we
Yeah.
need the data from the observation.
Right.
If our model is perfect, we don't need data assimilation.
Right.
But I mean, the reality is always here. So
Yeah.
we need the data assimilation to nudge the model
Right.
towards the reality.
But that's the different perspective, right? I mean, that's the perspective of the consequence what we are talking about.
Yeah.
It's triggered by the same lack of confidence in that part of the model.
Yeah.
Right?
Yeah.
Okay. All right.
Okay, so we usually assume that this adjustment data and it's not of consequence, but unfortunately, no. That's the point of my talk. So here, here I sidestep a little bit and then introduce what are internal waves. So internal waves I can describe here for this crowd, I can describe it as a perturbation that corresponds to a stably stratified medium. So we know that ocean and atmosphere are stratified media. The density changes with height. And then we can have waves in that. So usually waves, when we talk about waves, the visual comes into our mind is the surface waves, right? So surface waves is because it's an interface between two fluids, air and water, for example. And this interface is in equilibrium. And then when you have perturbation, it can oscillate. And then that creates waves. But if you have, okay, so if you have multiple interfaces like that, like one below the other, like in the case of stratified fluids, you can have waves in each of these interfaces, like the examples here shown here. So the blue liquid here is denser than the transparent liquid over here, and this guy is moving, giving a forcing, similar to like the tidal forcing, for example. And then there's a obstacle over here, or which this kind of gives a perturbation to the stably stratified system, which creates waves in this interface. This interface is within the fluid. That's why it's called internal waves or interfacial waves in this case. If it's a uniformly stratified fluids, you can have waves in each of these interfaces. So it can propagate horizontally as well as vertically downwards, like forcing the next interface below it. So those are that's the internal waves. And internal waves in the nature propagate with the frequencies set by the nature. There are two. One is the buoyancy frequency, which is the frequency set by the stratification itself, and the inertial frequency. Inertial frequency is set by the rotation of the Earth or whatever, the rotation of the system. And these waves can propagate only within F and N, these frequencies. The F is the lower bound and N is the higher bound of these frequencies. So in the ocean, we had two sources of internal waves mainly. There's two sources of energy for internal waves. One is the tidal motion, the sun and moon, the lunisolar tides. So these tides can create back and forth motions, which when those motions go over these seamounts, like the example that we showed before, it can create internal waves that can propagate vertically because it's uniformly stratified, and the ocean is stratified. And the other energy source is the wind. So the spatially varying wind can create oscillations in the surface layer, which can translate into the interior of the ocean. And because this wind does not have a frequency of its own, these motions obey the frequency of the rotation of the Earth, which is the inertial frequency. So these waves are called usually the near inertial waves, and the internal waves created by the tidal or internal tides. So these are the main two propagating internal waves in the ocean. And the reason why we are all interested in internal waves is that this is the main source of mixing in the interior of the ocean. So these waves propagate vertically through the ocean, and then it breaks. The wave always breaks up at some point, and then create turbulent mixing. And this turbulent mixing is essential for maintaining the large-scale circulation in the ocean. So the large-scale circulation, the warmer, lighter water, and the deep, colder water, they had to circulate at some point. And this turbulent heat diffusion, downward turbulent heat diffusion is contributed by the mixing caused by internal waves. Among other processes, but internal waves is believed to be the main process that causes these things. So that's like a short introduction to internal waves. So coming back to our problem, so there is a way to map all these motions that I talked about in the ocean in a nice, beautiful way. So this is one. This is that figures. So here, what I'm showing here is so these are all the different frequency motions, right? So we look at spectra. So what I'm showing here is the rotary spectra. Rotary because I take the rotary component of the velocities, the horizontal velocity U and V, and then take an FFT of them, of that. And then I do it for each grid point in my model, and then zonally average it, and then plot it like this. This here is the frequency, it's the cycles per day, and this is the latitude. So I can see the variation from pole to pole. And you can see different high frequency motions over here. So close to the zero frequency, you have the large scale flows with low frequencies. And then here, varying with latitude is the inertial frequency, F. And you can see the tidal frequencies. So there is a semi-diurnal tide, which happens twice per day. And then this diurnal tide happens every day. And then there are harmonics of these tides because there are different tidal cycles. And yeah, so this is a nice way to show all the frequency of motions in the global ocean in our model. And what I'm showing here is the simulation with data assimilation. And let me show you the simulation without data assimilation. Yeah, so it's the same a parallel simulation without data assimilation. And this is the difference of these two. So you can see that there is excess energy. So the spectral density corresponds with the energy, these motions. So there is excess energy close to the inertial frequency over here, and also close to the close to zero cycles per day. So these low frequency motions correspond with the spurious mixing or barotropical baroclinic adjustment, all those things that I talked about before. But as I said before, internal waves propagate between frequencies of F and N. So if it's above F, it can propagate. So this line over here and above that, the high frequency motions above that, these are propagating internal waves. And you see lots of spurious, or I would say spurious, like excess energy in this propagating internal waves over in simulations with data assimilation. Yeah, so this near inertial energy, yeah, this is the spurious near inertial wave energy that I'm talking about, just because you have data assimilation. Both have the same. So usually near inertial waves are generated by the wind forcing, and both simulation have exactly the same wind forcing. The only difference being that this has data assimilation. Data assimilation in the not in the wave frequency space. So it's only this temperature and salinity that is being assimilated, and you have this propagating waves. So, yeah.
Is the difference between them compared to the magnitude of the signals? How do you?
No. It's a
Log 10.
yeah. This is in log 10.
Oh,
sorry.
I was log 10.
Yeah. I mean, otherwise, I wouldn't say anything.
Oh, that's the thing. It's like 0.1%. Well, what's the? Because it's 10, and on the left is 10 to the 3, which is
Yeah.
1,000, right?
Yeah, sure. Like the whole, like the energy in the near inertial waves and the whole ocean is quite large compared to the North Sea.
Okay.
But I'll show you why this excess energy is important. So what I can do is that exactly like to understand how much of this is excess, I can integrate within this in near inertial range and then calculate the kinetic energy of these motions. And this is what I get. So this is simulation with data assimilation, This is simulation without data assimilation. This is the difference in kinetic energy. Yeah, still I have a long time. Yeah, but yeah, but I can. This is not low. This is the only average near-natural wave kinetic energy between these two experiments. And what we can see is that there is excess energy in the regions where we saw strong imbalances created by the updates. And I can calculate that there is 72% more near-natural wave kinetic energy in the simulation with data assimilation. So it's quite remarkable because the wind forcing is the same. So the only difference is that these updates are being added, and then you have these propagating waves. Yeah, that 72% is almost twice as much. And so these are waves, so it propagates. So I can calculate the flux of energy of these waves as well. So if I do that, so this is the map of the energy flux of near-natural waves, depth integrated energy flux. I don't have to say that this is the one with dA. Yeah, so this is what we expect from naturally occurring near-natural waves. The color here shows the wind input. So that's the power coming from the wind towards these motions on the surface. And then these the arrows are the flux of the energy. And these motions usually propagate towards the equator because that's the region where the F is lower. So it can only propagate between F and N. And here there are lots of noises over here. And then look at the size of the fluxes over here. It's quite huge compared to the naturally occurring natural waves. So the problem is with data assimilation, you cannot study any of these high frequency motions anymore if you have this kind of noise. And that's quite an important thing. So Earth system prediction, it's not just about forecasting hurricanes or anything. These models are being used to study physics of high frequency motions. These models are used as initial conditions for regional simulations to study short scale or high frequency motions in the regional ocean. Yeah.
So I have a question. So are you able to break the energy budget in terms of the excess energy between different components, different energies?
The different
Well, OLC, for example, right? I mean, you have different components in the energy. So,
Yeah.
you know, you may have acoustic perturbations of this kind, of the wave, of different kinds, right?
Yeah, so that comes up in the spectra, right? Because when I look at the spectra, most of the energy or most of the excess energy are concentrated close to X frequency.
So what is the physics behind that?
Yeah, so that's because, as I said, like any perturbation in a stratified system creates waves with the natural frequency of the system. So the natural frequency are either N, which is set by the buoyancy, or the F, the inertial frequency, if it's rotating.
So the buoyancy is one of the components that
Yes.
you can extract from it.
Yeah, but here it is in this large scale motions, it's the rotation of the Earth that sets the frequency. So that's why it's called near inertial waves. So if you throw a stone in the ocean, it creates near inertial waves, just like this. But yeah, if it's important, depends on the scale of the stone. Okay, so showing fluxes like this, we can do more, like because I have been working on internal waves for some time. I did all my internal wave analysis with the noise as well. So what we can do is that we can decompose this fluxes into vertical modes. So we know that ocean is only 4 to 5 kilometers deep, most of the places, but it's tens of thousands of kilometers wide. We can use this fact, so it's essentially a very thin layer of fluid to create an orthonormal basis of vertical structure functions or modes, vertical modes. And then we can project the velocity, the barochronic velocity fields into these modes to study the propagation of these motions horizontally. So the barochronic, the governing equation can be reduced with this approximation into a Sturm-Liouville equation. And then solving this will give me some eigenfunctions, which are the vertical structure function. And then I can project the eigenfunctions onto the 3D velocity fields I have, and then I get the modes. And so this, this is an illustration of the first 5 modes that I resolve with the resolution that I have. So the vertical structure is fixed by the eigenfunction, and I get the amplitudes to get the horizontal propagation. When I do that, and then I put all the variocollinear velocities into these eigenfunctions, I can create a map like this. So what I did here is the whole velocity is projected onto the modal eigenfunctions. And this is for the whole simulation with DA, the simulation without DA, the first 5 eigen modes. And again, the difference between the two. These are all rotor stuff, as I showed before. So what this says is that most of the noisy, spurious neural network waves project on the first mode, and this has a consequence, because the first mode has the least amount of vertical shear. It varies less vertically, so it does not dissipate that fast. So this is the most sustaining of the modes. So these first mode waves can propagate thousands of kilometers across the ocean, and also last for weeks. So we are talking about an Earth system giving out forecasts for 10 to 16 days, but with the noisy signals that can persist for weeks if the model is running. So that's a huge problem. Okay, so now I switch gear and then show a possible solution to reduce this noisy propagating waves. So this is the research that I did in COAPS for the last few months. So what we have is a different but a similar data assimilative system called Thesis. This is open source. The encoder that is used by Navy is not open source. It can be only used by Navy. So what we use in COAPS is open source 3D variational scheme for data assimilation called Thesis. And along with my collaborator Alex, I did some experiments in the Gulf of Mexico. So I chose Gulf of Mexico mainly because firstly COAPS is obsessed with the Gulf of Mexico, but this is an ideal space for studying this kind of things because it's a relatively low internal tides region, and it has lots of wind forcing but no tidal motions. So I can isolate the spurious neural network waves generated just because of DA, and then test. So it's a small region, so it can test different aspects of DA to see what produces the noises. So I did all these simulations. I'm not going in detail over there. I'll show the results. Yeah, so here I have a simulation without DA, and I have a parallel simulation with data assimilation. This is the kinetic energy in the neural network wave band. So without DA, the only reason there is energy here is the wind forcing. So there is a wind that generates the neural network waves here, and with DA there are more energy in that wave. This is the difference, and these are the energy fluxes for the simulation without DA and with DA. And as we already saw, there is strong noisy signals with data assimilation. So the 6-hour here correspond to the IAU period, the incremental analysis update period. So that means that the DA is being added to the system over 6 hours of duration. And so my goal is to isolate the spurious neural network waves from the physical neural network waves. So what I did was to have a simulation without wind forcing and without tides. So there is no physical reason for having internal waves in the system. But with data assimilation, we still have the spurious neural network waves. And the corresponding fluxes show that it's noisy. And So, and this is with the 6 hours of the IAE period. So you might have guessed what where I'm going with this. I increased the IAE period. Instead of putting it over 6 hours, I extended the amount of time where the increment is being added. So we tried 12 hours, 18 hours, but at 24 hours period, we reduced the noise. So here, this is a simulation without data assimilation, without wind, without tides. So there are no reason at all for having any waves of the sort. So yeah, clean ocean. And here, this is the 6 hour DA that I showed in the previous slide. And here, this is data assimilation that puts the increments over 24 hours and no wind and no tides. And this corresponds well with the free simulations without data assimilation. So here, in the near inertial band, you don't see any difference at all. But the important difference is that here you have data assimilation. So if you take daily means, this simulation corresponds more closely to the realistic ocean state, but without noises. So this is a ad hoc solution. So here, as a conclusion, so data assimilation with short IAE periods generate these propagating noises. So these noises are usually overlooked, mainly because data assimilative systems are used for studying large-scale motions, but increasingly, with the increase in resolution, they are being used for all kinds of other physical applications. So it's essential to reduce this noise over here in the forecast system. So a simple solution can be to increase the IAE period, but this is not that straightforward for a global system. The first slide that I showed, where you have the whole Earth system prediction data assimilating model, you have all kinds of models going back and forth and then giving first guesses. If you increase the IAE period, it increases the cost of running all this DA system as well. So there should be more studies to evaluate the cost benefit analysis of increasing this insertion periods. Yeah, thank you.
Thank you, Keshav. I'm really happy that I invited you. I learned many things, but I also learned that I'm training with the 6 hours AIU, and now they are going to complain. Any questions?
Maybe this is what you were trying to do with increasing the period from 6 hours to 24 hours. But is it possible to do, let's say it was possible to do data assimilation continuously? Because your perturbations are, you're shocking the system.
Right.
But if there is a way, let's say you could get data continuously.
Yeah.
Somehow.
It all depends on how fast you run this encoder, right? Like this. Right. Here. Yeah, see this data assimilation window. You're saying that data assimilation window should be as slow as possible, right? I don't think it will increase the accuracy of the data assimilation, because here most of the observations are quite sparsely located in time. So you have satellite tracks, ship data drifted track. I don't know what are these.
So maybe I'm talking. Can you go a couple of slides that when you did your cartoon? Okay, so here.
Yeah.
So like you're updating, your updates are happening at a certain amount.
Yeah, these are not every time step. It's just a data assimilation window. This is 24 hours for encoder.
So if those were closer together, reality wouldn't change much. Yeah, presumably. Yeah. Your model wouldn't change much, and therefore your analysis solution. So it's a series of small shocks.
Exactly. It could happen, but I don't know if for a global ocean model is it practical or not. But for an experiment, yes, there are data assimilation for fluid dynamics systems, especially for aerospace applications. You have like for the wing, like airfoil experiment, like the control, the turbulence control that you talked about. There is instantaneous data assimilation. That's how you control turbulence. So for ocean modeling, I don't know.
My question was similar, because I was thinking maybe that's due to the fact the Gulf Stream, we're taking all the observation for 24 hours, and then at noon we're like, okay, now you have to match this.
Yeah.
Now you're like spreading the perturbation across 24 hours, but what if we only take the observation like plus minus 1 hour, or something like this?
Yeah,
It
yeah,
might be already closer to the state of the model, like,
right.
hopefully.
Yeah. I don't know if it probably the Navy, not the Navy, the data assimilation researchers might have optimized how long the ocean data assimilation window should be to get accurate predictions of the ocean state in the forecast. In the forecast. I don't know how easy it is to reduce this window over here. Yeah, I mean, ideally, this should be, as you said, like if you had to implement what you said, it should be below, it should be smaller than the IAUP. Yeah, then I don't know if it's possible. Yeah.
So did you some evidence on the way the spurious waves are generated depending on the length of the window that you use for data assimilation?
Yeah.
So how does that depend? Is there any dependence?
Yes. Yeah. So depending on the length of the IAU.
Right. So how the energy that you are injecting is going to be distributed, because you are kind of exciting different modes, right?
Yeah. Yeah. So the reason why the energies, the spurious energy is reduced is because each subsequent increment is only a fraction of the whole.
No, I understand.
Yeah.
But when you force anything in the physical system with different frequency, and the frequency is somehow related to the period over which you are allowing the forcing to be applied,
right?
Then I expect that the system naturally has certain frequencies that will be excited more or less, depending on the length of the perturbation.
Yeah.
So you're injecting certain amount of energy, but with different rate, right?
Yeah.
Because of different length of the window.
Right.
So certain modes will be excited differently than other modes.
Yes. Yeah. Hopefully those modes are close to the realistic oceans. And then that's what we decide. And then the spurious modes are not excited.
So you know which modes are the most destructive.
I don't know.
You don't?
No.
I have a question. You mentioned how basically the magnitude of these internal waves makes the study of the small scale waves and high frequency events more difficult. Right? But I think on another slide you mentioned how internal waves of those magnitudes are critical for the mixing that actually leads to the more large scale flow of the ocean. So I'm curious if you've studied the impact of these spurious waves on large scale predictions and how they combine to influence your ability to predict things at the large scale as well.
Yeah, I haven't done that, but yeah, I'm sure that if you look at the mixing in this, in a simulation with like this kind of noise, I'm pretty sure the mixing is way off than the natural or the realistic mixing that we expect. So all these waves, they just not propagate; they will dissipate somehow eventually, and then this will cause spurious mixing. It's like a bonus energy to the system.
So in the data assimilation, one of the problems is the sensor distribution, right? I mean, you have sensors that you may distribute differently depending on the problem and optimize. So would the solution be to have better diagnostic for data collection for the regions that are problematic? Would that solve the problem?
Probably yes. Yeah, if you have more observations, yes. But the ocean is vast, so people are looking at including velocity, for example. Because velocities are not being assimilated in this model. It's only the temperature and salinity. So probably if you have more data, then you have better increments, which are kind of softer. I don't know. I cannot say for sure. But having more data might improve it or might not.
Well, because we are talking about the spurious effect, right?
Yeah.
So it doesn't mean that actually your spurious perturbation is going to be addressable.
No, it's not spurious perturbation. It's just that the perturbation is not realistic enough. And you're changing something in the large scale, like the temperature and salinity profiles, which will create some shocks to the system. that generates these noises. So if you have more small scale data, small scale or high frequency data that are being assimilated to the model, then probably the spurious energy might reduce. But how practical it is for the whole ocean, for the global system, I don't know. Because we have lots of data with the ocean right now that is being assimilated, but still it's not even close to the density of data from our model. It's still sparsely located. Yeah.
Any more questions?
I mean, there are like two distinct regions where the spurious oscillations are being created in the global model, right?
Yeah.
I mean, you could just increase sampling in those areas, right?
The reason is that those are the most sampled regions. So what you're saying is that, these regions over here, Gulf Stream, the whole US is, whole oceanography community in the US is putting all their assets over here.
Okay.
So, it's mainly because the motions are more the variability of the motions in these regions are more than the rest of the ocean. So here you have this Gulf Stream current that comes over here and then creates lots of eddies. Yeah, lots of eddies.
And also the
here you have a current called Kuroshio, which creates lots of eddies.
yes.
And then to fix all these eddies in place, you need the data. And then this creates shocks to the system, creating speeders.
So if you don't have this situation that you actually have infinite information about the real system and you feed that to your model.
Yeah.
Would that actually help or you will still create the shocks?
Yeah,
you know?
I mean, sure. Like, it's only if you can do that. There's no way you can. That's what I said. Like in an experiment, yes. If you have a tabletop experiment where you measure things from one location and then feed it to the modeling of that system, then yes, you can do that. And then we can do that for optimal control of dynamics problem. But for ocean, it's too vast, and then we are only 8 billion, so it's not enough for measuring all the ocean.
Keshav, everything that you show is 3D bar, right?
Yes.
So that's 3D interpolated at specific times. So if you increase the resolution, you have smaller errors. If you use a 4D bar with interpolation of time, how computationally expensive that would be to run a global one? Like I don't know if the Navy uses already 4D bar.
Navy does not use it for the whole global ocean model. They use it for regional model for ENCOM. And I don't know if they have reduced spurious waves or not. I haven't used a 4D system to calculate these kind of things. But NEMO has 4D data assimilation. So I don't know. I don't know if it reduces, but it might be. Yes, but
okay. So let's then get speaker again.